Hey guys, Mr. T here, another video. So this is still in exercise 90.1, 90.2, where it's talking about describing the distribution of his data set. I figured I'd do a separate video here so it'd be more useful to me in other situations. I could use it for other subjects. So, the last thing we spoke about was numerical data. What's special about numerical data? It has a particular order, numerical order, because you count numbers. They go from small to large or large to small. They have a set order. They mean something in order. So you can talk about the shape of data that's numerical because the shape is meaningful. It means something because each bit of data has a relation, has an order to each other. So the following terms that we're going to be talking about are only going to apply to numerical data because it has that order. If you can't talk about the shape of categorical data most of the time. Maybe if it was ordinal, but even then the order, it's because it's words, it's really, you're stretching to get meaning out of that. The shape of categorical data really has no meaning because the categories have no particular order. Let's say you were drawing the number of people with different hair colors. One day you might decide to put blonde first, one day you might decide to put black first. It really doesn't matter, they have no meaning compared to each other. There's no order to that, so talking about the shape of it would mean nothing. But in this case we're talking about numerical data, so the order does mean something, so the shape that we see is meaningful. So here are three terms we can use to describe the distribution of data. And so the first is symmetric. Sometimes it can be helpful to draw a curve over the data to help you see the shape. So symmetric bit of data has a central peak there in the middle, and both sides of the middle are shaped similarly. So that side looks very similar to the other side, so you would call that symmetric. Why is it symmetric? Because it looks symmetrical. The other shape here we've got is negatively skewed. I'll draw a curve through that. So you can see the hump is to the right side, and the right side is the higher numbers. So higher, you're getting higher as you go to the right. So what a negatively skewed graph is more of the data is concentrated on the high end. High end, more data. Why is there more data? Because frequency is in the vertical direction, so you've got more values that are larger on the high end of the data, so it's more concentrated there. And the other thing is you can see on the lower end stretched out, stretch on lower end. Alright. Now the opposite to negatively skewed is positively skewed. This, you have the peak, so the concentration of the data on the low end. Not data. I accidentally wrote that wrong. More data on the low end for positively skewed. So it's sort of opposite of what you would think. Positively sounds better, so you would think that the more of the data would be in the high end, but no, it's the opposite way. Positively skewed has more data on the low end here, and it's stretched on high end. Alright, so you've got more concentrated of the data on the low end of the values, and there's the higher end stretched out. And negatively skewed, you've got more data on the high end. So you can think of it as being slightly opposite to what you might think of with the terms. The last thing I need to talk about to do with shape is outliers. So you may have heard of these in science. Outliers are data values that are either much larger or much smaller than the main body of the data. The main shape of the data you'll have, you might describe it as positively skewed, negatively skewed, or symmetrical, but then you'll find there's little bars on your representation or little bits of data really far away. That's an outlier. So in a graphical presentation, outliers are obvious as they're separated from most of the data, so you've got a low end outlier, got a high-end one here. This is the main body of the data here, but you've got data values extremely high and extremely low. That would be classed as outliers because they're exceedingly different. So the only thing that is important here is the fact whether you should discard them or not, whether you should ignore the outliers or not. And how do you decide that? If an outlier has happened or has arisen due to a mistake in the method, so you've messed something up, or you did an error in collecting the data, you accidentally typed in something wrong, you can pretty much ignore it. You can just remove it from your data and just pretend it didn't happen. Okay, if you can guarantee that a mistake was made and you reference it in your analysis or state it, then you can say, okay, because we can acknowledge that this outlier, this bit of data was from a mistake, I accidentally put too many zeros or something, then you can just ignore it. You can cross that out and go, okay, my data is actually this, therefore it is definitely negatively skewed, or something like that. You can talk about the rest of the shape, and you're ignoring the outlier. But if you cannot properly provide evidence that it's from some sort of mistake, if you can't prove that there was a mistake that happened that caused that outlier, then it's a genuine result. It's not an outlier anymore. It's a legit result, so you have to keep it in the data. You can't ignore it, and you have to show that it occurred. So if I don't have any information showing that I accidentally put an extra zero there, and the best I can do is say that that was actually a legitimate score or a legitimate result from my testing, you have to leave that there and show it, and you need to try your best to explain why that occurred, why that bit of data could have happened. Alright, so that's outliers for you. Hopefully that helps you out in your understanding, and I'll see you in the next video.